Camera's good. We're
Yeah.
excellent. Is it recording?
It's rolling.
It's rolling.
It's been rolling.
It's been rolling. All this is going in, by the way. Awesome. So, could you introduce yourself for those interested?
Yeah, so my name is Lucas Meza. I am assistant professor of mechanical engineering. I started in the department in January 2019, so I've been here for about 5 years now. Yeah, and I work on mechanics of materials. So
Okay.
I study how and why stuff breaks.
Okay, I want to ask a little bit, going back, I want to ask about kind of like where you started from, like your upbringing, where you're from, how you got here, essentially.
So I grew up in Oceanside, San Diego. I didn't have any particular background or experience with engineering growing up. I think I had a grandpa who was an engineer, but never really met with him at all or talked about engineering. Neither of my parents were. In high school, I was just kind of interested in math and physics and knew I liked building stuff. And so kind of chose mechanical engineering almost on a whim. Not on a whim, but, I was like, that seems like it'd probably be a good fit. Started doing it, going into undergrad, and just all of the subjects really clicked. So everything, solids, materials, heat transfer, not thermo. That's the one that was not big on, but controls, kinematics, design, CAD, all of that. All of it was really fun. It all fit really well with kind of how my brain works, things that I was interested in. I sort of ran with it.
Where did you go to college?
I was at UCLA.
Mm.
Yeah.
Did you get a doctor? Did you get like a master's or something?
Yeah. So I did UCLA for undergraduate and then Caltech for master's and Ph.D.
And then did you move up here in 2019?
Then we did, so I finished my PhD 2016 and I did 2 years of a postdoc in Cambridge, the UK one.
Okay.
Yeah.
What was that like?
That was fun. It was nice getting international travel experience. I hadn't lived outside of Southern California, so living internationally was interesting. It's a very different academic culture, and I think that is part of what helped inspire why I wanted to be one back in the U.S., but then also the University of Washington in particular. So undergrad, I had a little bit of research experience. I got a couple quarters working in a lab. I did a lot of student project work, but then going to grad school is really when I started doing research, and that's when I found the topic that I'm now working on that I was really interested in. But Caltech was a very small school, so it was a very collaborative environment. There was maybe 3,000 people total in the school, undergrad, grad, professors, so teeny tiny. And so you knew almost everybody, you knew a lot of what people were working on, and it was really easy to work with other people. And that wasn't necessarily the environment in Cambridge. There was lots of really brilliant people, but it was a little bit more siloed. So University of Washington is a huge school, 50,000, 60,000 people.
Yeah, more than 3,000.
Yeah, a little bit more than 3,000. But that collaborative spirit or the collaborative environment is really thrives here. We're a really innovative school. We're one of the top 10 in the country in terms of innovative output, like getting patents and companies and spin-offs. And that comes through in how easy it is to work across different borders, different boundaries in the university. So I collaborate with people in chemistry and physics and the medical school, in different engineering departments. And that's been, everybody's kind of interested and eager to work across fields.
Do you do any research here?
Yeah, so I run a research group. That's most professors, unless they are teaching faculty or research faculty. Unless they're teaching faculty, they run labs, and that's actually the primary thing that we are brought here to the university to do. So I have a group of currently 5 PhD students, 3 master students, and a handful of undergrads that are kind of in flux. That's most engineering faculty run research groups.
What kind of research do you do?
So I study nanoarchitected materials. So mechanics of materials very broadly, how and why stuff breaks. And I look at that, 1, at the nanoscale, so I make and break teeny tiny things. And then 2, I try to study how structure affects function. So for example, foam. Like a foam is made of materials, but then it is a structure. It's kind of a random bubble structure, but that changes what the properties are. If we make something into a lattice or into a fiber composite or into into a honeycomb, that those are all tools that we use to change properties. Even things like the clothes that we're wearing. These are all of our clothing is made out of fibers, individual fibers that are woven into a fabric. So the way that those fibers are woven together, the types of stitching patterns, the thickness of the fibers themselves, all changes how that fabric responds. So all of these are architected material concepts. And it's used kind of ubiquitously in engineering, everything from the brick walls in the room. Brick is a material, but brick and mortar then becomes a composite material. Natural materials, wood is a composite. Literally every natural material is a composite, but wood, you can see like the fiber structure of the wood really clearly. And we use a lot of those principles in engineering, and that's what I study, but at teeny tiny scales.
At really small stuff, like in nano or like in micro stuff.
Both.
Oh,
Yeah.
That's really cool.
Yeah, so we make things out of nanoscale components, and then eventually you build those up and you end up with microscale or potentially millimeter scale components. And that is about as big as I get.
So is this
so millimeter is pretty large.
Yeah. Is this for like electrical components or for like carbon nanotubes?
So we do make carbon nanotubes. I have a project where we've been fabricating those. We are really trying to study fundamentals of material physics. So I'm in mechanical engineering, but I do mechanics of materials. So I kind of balance that material science, or skirt the material science mechanical engineering line. I really try to understand, like, at a very fundamental level, why do materials behave the way that they do? What does it mean to have a fracture toughness? What does it mean when a material is yielding, plastically deforming? And when you study things at the nanoscale, you can see, metals have plasticity via dislocations, and you can see the individual slip events happening at the nano and micro scale. You can see polymer crazing, like polymers are molecular spaghetti, and you can see those molecules tearing apart when you apply tension to them. And you can only understand that when you look at materials at these very small scales. So we have applications in biomedical devices, in composites for aerospace components. We're trying to do some work with Boeing, with Packard, the truck company, with a handful of different industries. But really where the space that I like to live in is that much more fundamental science regime. So really trying to understand the world a little bit better, less focused on applications.
So I want to ask you, have you worked in the industry before?
Define the industry. Have I worked in an industry before?
Sure. Have you worked at McDonald's? Have you worked in an industry before?
I worked at Big Five once.
Oh, okay.
No, but I did some internships at Sandia National Labs. So I worked in their telemetry division, making devices that flew in airplanes. Turns out airplanes up in the sky get really cold, but it's hard to know what temperatures they end up at. And a lot of the sensors we have don't really work well. You can't just like throw a thermometer in there because it'll also freeze over and the electronics will stop working. So we built devices for that. But I think I was reasonably good at that. I also did student projects, not in industry necessarily, but working on like building a product. But I really like taking time and thinking about problems. And I think that was where the pace industry looks for turnover, creating products, designing, making something, and then building it and shipping it off. And I like having the freedom to take time to understand why we're doing what we're doing, why things are behaving the way that they are. So I kind of liked working in academia more because I had the time and flexibility to think more deeply about problems.
So you feel like you were drawn more to research than working in the field? Yeah.
Yeah.
Okay.
Which I got a flavor of working in a research lab in undergrad. I think I could have done pretty well and been happy in different industries around. I was again probably going to go for national lab work if I went to industry. I don't know if it's like industry.
That's industry.
Yeah. Defense industry.
Sure, that's industry.
Yeah. Although national labs are technically funded by the Department of Energy. That's where nuclear defense happens. Yeah.
Oh boy. Wow.
Yeah. Anyway. So that was an option, a career path. And I kind of took a gamble with a Ph.D. had a hunch that I would enjoy it, much like getting into mechanical engineering to begin with, and then ended up doing really well, which is why I'm here.
There you go. Do you feel like you were always drawn to teaching as well, or was it mostly for the research opportunities?
Yeah, no, I also worked as a tutor in undergrad. I taught all of the different math and physics classes that UCLA offered. I worked for a tutoring group for 2 years, and in that, UCLA is also a quarter system, so every quarter was like a different class or two. So I kind of taught almost all of the different undergrad math and physics classes at some point. And so I knew that I enjoyed that aspect of it. And like being in doing a PhD, you have the option to go and do industrial research, like in an R&D wing of a company. You could start your own company. You could try to run spin-offs, run startup companies, or you can go into the academic route, which is actually a small percentage of people who get PhDs end up in that route, partly because it's really competitive, partly because not everybody likes teaching. But I knew that was something that I wanted to try for. So, yeah.
All right, cool. I want to kind of tack a little bit here. What would you say to kind of a prospective engineering student, someone not sure what they want to do, really? How would you push them in the direction of engineering in general, or mechanical engineering?
Yeah.
Or material sciences?
Yeah. So, assuming that somebody was interested in some sort of STEM, the line that I like to draw, scientists study truth in the world. They try to understand what is the reality of the world that we live in. Engineers figure out what to do with it. So everything around us, every component, TV, camera, cell phones, cars, planes, buildings, the roads, literally the entire world around us was designed by engineers, made by technicians and manufacturers and people, not necessarily engineers, but it was designed initially by engineers. So engineers are the people who make the world work. It's a lot less. This is also where my interests are, kind of skirting that material science, mechanical engineering line. I'm interested more in the fundamental nature of the world, which is why I like to play in that regime. But engineering is, okay, I know this well enough. What do I do with it? Make a thing, throw in a factor of safety, call it good. Yeah. And so that mentality, though, of I need to make a product that solves a problem, that does a thing. That's what engineers do. And it's literally every industry you can think of. So mechanical engineering makes all the things that move. Generally, this is, robotics, it's power plants, it's cars and planes. Civil engineers make the stuff that doesn't move. So the buildings around us, the roads, the water treatment plants. Environmental engineering is wrapped up into civil quite often. Earthquake engineering, civil infrastructure reliability. Chemical engineers design all of also power plants, but things like chemical processes for gas and oil or pharmaceuticals. Those all have chemical engineers behind them. Bioengineers, all of our medical devices, the bolts and plates that go into your arm when you break your arm, when you get a fake hip or an artificial hip, trying to create synthetic tissues, 3D printing tissues. It's all bioengineering. Computer science and electrical engineering are building all of the hardware and software that goes behind the electronics world that we live in. So again, literally everything around us is made by engineers at some point. So if making stuff is what you're interested in, then engineering is the right way to go. If it's understanding the world more deeply, then it's physics, chemistry, biology, some of the more fundamental sciences. But that's where that line is. We don't care necessarily about why the world is what it is, but we try to do what we can with it.
Do you think engineering is the future, or is it like CS or something more?
You mean mechanical engineering?
Sure.
So I think there'll always be a need for all of these different engineering disciplines. Some will ebb and flow in terms of popularity. Mechanical engineering is an incredibly diverse discipline. So mechanical engineering houses controls, robotics and mechatronics, heat transfer fluids, statics, solid mechanics, mechanics of materials. All of those kind of live in mechanical engineering, and all of those have a million different applications. So the mechanical engineering department I would actually argue is one of the most broad disciplines in engineering. Other departments focus more specifically on a subset of topics. But yeah, so I don't think mechanical engineering is a discipline because of that. It literally touches so many different areas of the world around us. It's going to stay in fashion for a while. Obviously, computer science and electrical engineering, as we further digitize the world, as we get deeper into the internet and technology, we'll need more and more software and hardware side of engineering. But that doesn't mean that we're not going to need to build buildings and make roads and make planes that are more reliable, cars that don't crash and burn. Even our phones, when you drop your phone, why doesn't it break?
OtterBox.
There's an engineer behind that.
Wow. Someone printed this. Oh man.
Yeah.
It's awesome.
Or cast it or thermoformed
You're
it.
probably right.
Yeah.
Kind of the inverse side of people coming into college, right? Deciding where they want to go. Mm-hmm. What advice would you have for people leaving engineering, right? Going into the job market? What's the best way to look for internships and by extension jobs, I assume?
Yeah. So getting a job, the most important thing to do for getting a job is to get a network, to either a network of this. It sounds like an intimidating word, but it's literally just making friends with people who are going to be in different engineering or whatever fields. That is networking in a nutshell, is go talk to people and get to know them. And, people are people and we like to hire people we like to work with. So networking is vitally important. One of the best ways to do that is through internships. So before the point of graduating, try to get as many internships in as you can. Those are direct avenues to more permanent jobs, but also just, again, building your network, building the number of people you know, working in whatever industry. Outside of that, I think student project teams are actually one of the most valuable things that people can do. So I worked in undergrad on a Baja SAE team, so we made off-road race cars. Very different world than the nanomaterials I work with now.
Yeah, wow.
That was a thing that I did. And that gave me a lot of engineering project experience that you don't get in classes alone. So it's multi-year projects. You have people who have been there for multiple years. You have kind of a history of your program. And so these kind of longer term, larger scale engineering projects are really what engineering is. We have a product we're trying to make. We have a team of engineers who you need to work with to get it out. And how do you work with people in a team? How do you collaborate together? How do you get past problems? Classwork gives you the fundamentals. It gives you the tools to get past those problems, but it doesn't give you that experience necessarily. And you see it in capstones, but that's all the way at the very end of your career in academic career in undergrad. So student project teams at the UW in just mechanical engineering alone. There's Formula SAE. There's I guess SARP is the advanced rocket propulsion team, sort of in aerospace. We have the Hyperloop team. We have Husky Robotics.
F1. There's a lot of them.
Yeah.
Right?
So there's all kinds of different interesting projects that you can get involved in, and students can make their own. Like new RSOs pop up all the time. Don't necessarily always stay around, but there's some big, very well established ones directly associated with engineering, mechanical engineering, but then also across other departments.
Do you think that network is more important than the student clubs? If you had to put a price on each one?
They're coupled.
They're the same. Oh.
You're making a network when you're working with the student team. Yeah. A lot of the people that I was working with and when I did Baja, I still keep in touch with today. They're engineers working in the field. We had people go work for SpaceX, for GM. I had a friend end up at Caltech with me at the time, who's now off in a different industry. But you build that network of people who are going to end up somewhere and who you can maybe pull on if you need a job in the future. Not all the time, but the more people you know, the more opportunities there are.
Do you know a lot of the people in like the Seattle industry area?
Getting to know them better. I do a fair amount of work with Boeing currently. So the mechanical engineering department has the Boeing Advanced Research Center, BARC. So we we collaborate a lot with Boeing folks. And I have some people from my group who are now employees at Boeing, former people in my group who graduated and went off to Boeing. Some folks at not SpaceX, Blue Origin, the one that's in our backyard. I know a handful of people at PACCAR. I'm starting to try to build some of those industry connections. It takes a little bit longer. Professors are busy and balancing that, running a research group and networking, games, and teaching at the same time. Yeah, there's a lot of balls to juggle.
I'm sure you're very busy. Yeah. I'm busy because I have this huge essay to write due tonight.
But some great professor gave you.
Some professor just gave me this.
The one hobby that I actually do, that I used to do a lot, that I do less now, is cooking.
Oh.
So,
that's awesome.
I really enjoy cooking as a hobby because it's a hobby you can eat when you're done, which is always nice.
Sure.
There is a lot of material science in cooking. It's like soft matter physics, phase transitions, foaming. All of your food is architected. Yeah. So I tend to geek out on the science side of food. And there's a lot of other fellow nerds out there who geek out over food stuff, food science. A lot of which is happening in Seattle. Seattle is actually a nice hub for it. So
that's fun.
That is something I like to do. Try out new recipes. Try out like interesting things with food. Just try to understand what we're eating more deeply. I'm also big into getting outdoors. So I like biking, hiking, rock climbing. I don't do them as much as I want to. Don't have quite enough time. But the Pacific Northwest or Seattle, this whole area is incredibly beautiful all the time. A little bit chilly and wet sometimes, but minus that, it's a really nice place to get outdoors and see just the beautiful surroundings. And Seattle is awesome because you drive 30 minutes and you're in the middle of the forest.
That's super fun. The last professor I talked to, I asked him the same question. He said, I love cooking and I love going outside.
Clearly I fit in well.
I just thought he was a civil engineer though, but
birds of a feather.
That's
also what drew me to Washington.
Yeah, I think that's what I think you'll find a lot of people in common in this area. I love going outside and doing things of that sort. It's just one of the best places in the country to do things like that. Yeah.
Hard to argue with that.
Okay, you ready? Here we go. I'm gonna throw a really long shot here.
Yeah.
Okay. Who's gonna win? Mike Tyson versus Jake Paul. It's tonight. This is gonna date the recording, but
it is tonight.
It's tonight.
I don't know. The fact that it's like he's 58 now, 57. The fact that he's still like getting into a ring and boxing, like I don't know. I just don't want anybody to die. That's.
I don't want Jake Paul to die.
Yeah,
I know.
He can probably take a few more hits. I don't know.
Okay.
He's still young enough. 27.
Yeah.
Something.
It's a bit of a gap.
Yeah, a little bit. Fighting your grandpa might be a little weird. But who knows? My grandpa might win.
Yeah, I guess we'll see. All right, we're locking in your prediction. Okay, we're gonna edit that in post-fight to see who wins.
Great. Now Mike Tyson's gonna hunt me down.
Yeah, exactly. Mike Tyson calls you out on. Well, it was great to talk to you, Professor Meza.
Yeah.
Thanks for coming in, and
thanks for inviting me.
Yeah, maybe we'll talk again in the future.
Yeah.
Or I'll see you in class on Monday.
That.